Hello, and welcome back to AIT 1001. Today we're on Lesson 8, Series Parallel Circuits, and this is the last lesson in the AIT 1001 class. In this lesson you're going to be constructing series parallel circuits using various components. This will be much like the labs you did for the series circuit lab, the parallel circuit lab, except now you're going to be constructing series parallel circuits. You're going to be calculating the total resistance, voltage, and current in a series parallel circuit, and you'll be doing this in the online content and in the lab environment. You're going to calculate the total capacitance in a series parallel circuit. This will be done in the online material. The textbook goes into an explanation of this, but we're not going to actually be building the series parallel capacitance circuits in the lab. You're going to analyze series parallel circuits using a digital multimeter. And again, these are the three main things you're going to be doing in the lab. You're going to be constructing the circuits, calculating the values throughout the circuit, and then analyzing the circuit using a digital multimeter to confirm that these values are indeed correct. You'll be designing a voltage divider circuit. Again, that's in the online content. The textbook goes into an explanation. The purpose of a voltage divider circuit and how to construct them and what they're used for. Essentially, if you have a given power supply voltage, say it's 24 volts and you need 24 volts in one part of the circuit and 5 volts in another part of the circuit, you can design a voltage divider network that has different voltages at different points, and so you can use those in other parts of the circuit. But like I said, the textbook kind of goes into a pretty good explanation of what voltage divider circuit is and what they're used for. And then finally, you're going to explain the purpose of a Wheatstone bridge. Again, the textbook material goes into what a Wheatstone bridge is and what they're used for. Essentially, it's a sensitive circuit using a resistor network to determine the resistance value. So your multimeter that you've been using to measure resistance of resistors and circuit components in a circuit actually has a built-in Wheatstone bridge to be able to determine those resistance values. But like I said, the textbook will go into more in-depth and more explanation of what that is and how it does what it does. For the purpose of this lesson, this presentation, basically we're going to take a series parallel circuit and we're going to break it down by voltage, current, and resistance using Ohm's law and how to do that throughout the circuit. So for series parallel circuits, here's an example of a series parallel circuit. And this is a series parallel circuit in that it has loads in series, but it also has some parallel networks built into in those loads. So I've got a DC power supply here. I've got a selector switch to power the circuit off and on. I've got a resistor here for a load, then two resistors in parallel for another load in series with my first load, and then back to the power supply. So if I was going to plug some values in here, we'll say I'm going to have a 500 volt DC power supply. And just this example, we have a DC power supply, but again, Ohm's law doesn't care if it's AC or DC. All it cares about is what the value of that power supply is. R1, the first resistor in my series parallel circuit is 100 ohms. And then down here in my parallel network, I have a 1K ohm in the R2 location and a 750 ohm resistor in the R3 location. So this is the circuit that we're going to be analyzing, and what we're going to determine is total voltage. We're going to determine total voltage in this circuit, the total resistance in this circuit, in this series parallel network. We're going to determine the total current through in this circuit. We're going to determine the voltage across R1, the voltage across R2, the voltage across R3, the current through R1, current through R2, and the current through R3. So we're going, with the information we have here, we'll be able to determine all these values. So the first thing is total voltage. So my total voltage equals the supply voltage, and that is given to us in the schematic. So my total voltage is 500 volts, and like I said, no calculations there is provided. So that's a first bit of information that we've determined from the schematic. The next thing we want to determine is the total resistance. And like I said before, it's a series parallel circuit, so I have loads in series, and then this with a parallel network built in to one of the loads. So to break this down and to figure all this out, the total resistance of a series parallel circuit is the sum of the total parallel resistance plus the series resistance. So what I need to do is determine my total equivalent resistance for this parallel network, and then add it to my other resistors in series, which in this case is R1. So like I said, first thing I want to do is determine my equivalent parallel resistance here. And going back to lesson 7, where we looked at how to determine parallel resistance, we use this formula right here. 1 over RT equals 1 over R1 plus 1 over R2, so on and so forth, depending on how many resistors we have in our network. So if I was going to plug these values in, my total parallel resistance equals 1 over RT equals 1 over 1000 plus 1 over 750, because this 1 k ohm, I converted it to my base unit, so my bottom units here, or my resistance units, are at the same unit, no prefixes. So this becomes my formula to figure out the total equivalent resistance here. So carrying that forward, and as I said before, I personally don't like working with fractions, because in this case we're going to have to determine, if we stayed with the fractions, we'd have to come up with a common denominator between 1000 and 750, and that could run up into some pretty large numbers to be able to find a common denominator. That's why I find it easier to just simply convert these to a decimal equivalent and then work the fraction, or work out the formula, and it's a lot easier and a lot fewer steps. So if I take find my decimal equivalents, 1 divided by 1000 gives me 0.001, 1 divided by 750 gives me 0.00133. So now I'm just simply adding my decimal equivalents together. So I come up with 1 over RT equals 0.00233, and the 333 is just carried out. I just chose not to take it any farther than 2 3's on the end there. So carrying that forward, if you remember when we did parallel circuits, all I want to do is just move this 1 over here and leave RT by itself. I've done that. So now my total resistance becomes 1 divided by 0.00233, or RT equals 428.57 ohms. So all I've done so far is taken these 2 resistors, I ignored everything else, and just looked at these 2 resistors by themselves to come up with my total equivalent resistance for this parallel network. So these 2 resistors in parallel equal 428.57 ohms. So now I know my total parallel resistance. Now I want to find the total resistance in this circuit. So simply, now we go back to our series formula where I just add the resistances together. So my R1, which is 100 ohms, I add it to my equivalent resistance here, which is 428.57. So that becomes this simple addition problem here. So now my total resistance for this whole network here is 528.57 ohms. So from here to here is my total resistance, and that's what it should be now. Now that I know my total current, or now that I know my total resistance, sorry, I can find my total current, because my total current I can find by taking the total voltage and dividing it by the total resistance, and that gives me the total current for this entire circuit. So if I take my 500 volts and divide it by my 528.57 ohms, that comes up to be 946 milliamps. So the total current in this circuit is 946 .946 amps or 946 milliamps. So I can find that through any part of this circuit except for the parallel, where these two branches will actually divide that current between the two parallels, or between the two parallel branches. So part of that 946 will go through here, and the other part will go through here, but combined that will equal the total current in the main branch. So moving forward, now that we know our current, our total current, we know our total voltage, we know our total resistance. So now let's start breaking it down over each load to find out what our total current and voltage is at each point. So the first thing I want to do is find the voltage drop across R1. Well, I already know the current through R1 because this part of the main branch, there's nothing in parallel with it at this point. So the current through R1 is going to equal the total current because it's on the main branch. And we determined that was 946 milliamps or 0.946 amps. So I can determine the voltage drop across R1 by taking the current times resistance. So I take the 0.946 amps, so I had to convert the milliamps back to amps because when I'm using Ohm's law, I have to use the base units. So the voltage across R1 becomes 0.946 amps times 100 ohms, or 94.6 volts. So the voltage drop across R1 will be 94.6 volts at this point in the circuit. So what's our voltage across R2 and 3? Because they're in parallel, so they're going to have the same voltage across them, but they're going to have different current values. So to find the voltage across R2 and R3, I take the current times the resistance. So our current again was 0.946 amps, and our resistance, we take the equivalent resistance that we calculated earlier to determine the voltage across this network. So if I take the 0.946 amps times my 428.57 ohms, which is what I determined was here, that shows that I've got 405 volts, or 405.4 volts dropped across these two resistors. So at this point, I'm dropping 96.4 volts, and from here I'm dropping 405.4 volts. So now we know the voltage at this point. So now we can determine the current through each resistor. So our voltage we determined was 405, excuse me, 405.4 volts at this point. So now it's just, I take the voltage divided by the resistance, so that tells me how much current I have flowing through R2. So I take the 405.4 divided by my 1,000 ohms right here. So I have to convert this to the base unit using an Ohm's law. Take it divided by the 1,000 ohms. So I determined that it's 405 milliamps or 0.405 amps flowing through this resistor in this circuit. In R3, it's the same thing. I take the 405.4 volts divided by my resistance of 750 ohms. And it comes up to be 0.541 amps or 541 milliamps. So we've just, at this point, we've determined our voltage, current, and resistance everywhere in this circuit. So our total voltage we determined was 500 volts. Total resistance for this network is 528.57 ohms. The total current in the main branch from here to here is 946 milliamps. The voltage across R1 was 94.6 volts. The voltage across R2 is 405.4 volts. The voltage across R3 is also 405.4 volts because they're in parallel, have electrical continuity between them. The current through R1, since it's on the main branch, it's 946 milliamps. Current through R2 is 405 milliamps, and the current through R3, 541 milliamps. And again, if we wanted to confirm this, if we added the 405 to 541, we would come up, because this is these two should combine to equal the total current. And if you add the 405 and the 541 together, it does come up to be my 946 milliamps. I'll get it out here in a minute. And to determine if my voltage drop was accurate, I had 405 volts here, and I had 94.6 volts here. So if I add the 94.6 and the 405.4, it equals my 500 volts. So that just confirms that the circuit has been, that the calculations we made were accurate. So if you have any questions on how to calculate or how to break down a series parallel circuit, please post them in the discussion board. Call my office, stop by my office anytime, and if you have any questions, let me know. Thank you.